In an earlier session, we discussed about the mathematical objects that appear in Newton's second law of motion. In particular, we talked about the quantities which are known as vectors. In your school, you may have studied that vectors are mathematical objects having both magnitude and directions. For example, the position vectors or the velocity vectors both have some magnitude as well as some spatial direction. However, is it always true that a vector necessarily needs to have some spatial direction? In today's session, we begin our discussion on the topics of vectors and vector calculus. Let us consider two vectors as you see it here, A and B. Now, if we add these two vectors A and B, then we get another vector, let's call it C, as you see it here, which is 7 times I cap plus 6 times j cap plus 8 times k cap. And such operations are known as addition of vectors. So in other words, vectors can be added to get another vector. Now we can ask, what are these numbers 7, 6, 8 that appear in the expression of the vector C? You may answer, these are the real numbers. As you have discussed earlier, these numbers are also known as scalars. Additionally, we have seen that a vector can be multiplied by a scalar number. For example, if you multiply the vector C by 2, you get another vector. Let's call this vector to be D, which is then given by 14 times I cap plus 12 times j cap plus 16 times k cap. And such an operation is known as the scalar multiplication. For a change, let us now consider a polynomial functions of degree 2. Let us consider two functions f of x and g of x as it given here. So now you see that if I add these two functions f of x, g of x, and let's denote this new function to be h of x, then as you can see, h of x is 3x squared plus 7x plus 6. And if you look at the form of the function, this function is also a polynomial of second degree as the function f of x and g of x. Now, what happens if I multiply the function h of x by a scalar number? Let's call this function to be h1 of x. Then as you can see, h1 of x is 6x squared plus 14x plus 12, which also happens to be a polynomial of second degree, as the original function fx and gx, or like the function h of x. Let us now rewrite the vectors A in slightly different form. Let's rewrite the I cap as E1 cap, j cap as E2 cap, and k cap as E3 cap. And also let us denote A1 to be 3, A2 to be 1, and A3 to be 2. Then the vector A, as you see it here, can be expressed as little a1 times E1 cap plus A2 times E2 cap plus A3 times E3 cap, as you see it here. Now similarly, if I consider a polynomial of degree 2, the function f of x, and let us write it as E1 to be x squared, E2 to be x, and E3 to be 1. Then if you look carefully, then you see that even the f of x can be written in a form which looks like a vector. We know A is a vector. What about the f of x? Because it seems to satisfy the properties of A. For example, if you add two such functions, it gives you a function of the same kind. If you multiply by a scalar number, again it gives you the function of same kind. Can you also view the function f of x as a vector? The answer turns out to be yes. If f of x is a vector, then you can ask me, what is the direction of f of x? Does it have a direction like a position vector? Clearly, we need to define vectors in a manner which goes beyond the objects having only the magnitude and the direction. Now I am going to introduce the concept of linear vector space. A linear vector space V over the real field R or the complex field C is a set with two operations, namely addition and scalar multiplication, such that following properties are satisfied for all UVW which belongs to the vector space V and ABC which belongs to the field R or the complex field C. And the properties are, the number one is called additive closure. That is, if U and V are two vectors that belongs to the set capital V, then if you add them, the result should also be a vector which also belongs to the same set capital V. The second property is called additive commutativity. It doesn't matter whether you add U to V or you add V to U, the resultant vector should be the same. The third property is known as additive associativity. In other words, if you have three vectors and if you add the second and third first and then you add the first vector to it, the resultant vector should be same if you add the first to the second vector first and then you add the third vector to the resultant vector. The fourth property is known as the existence of null vector. So null vector is an element of the set capital V. So for example, if you add null vector to another vector, say U, then the result is again U. The fifth property is known as the additive inverse. For all vectors U, there exists a vector V such that if you add U to V, resultant vector is a null vector. The sixth property is known as the closure of scalar multiplication. That is, if you have a vector U in the set capital V, then if you multiply the vector U by a scalar number A which belongs to either real number or a complex number, then the resultant vector is also a vector that belongs to the same set V. The seventh property is known as the scalar multiplication is distributive over vectors. That is, if you multiply an addition of two vectors by a number A, then it should be same as if you multiply the individual vector by A and then you add. The eighth property is known as the scalar multiplication is distributive over scalars. That means if you add two numbers A and B and multiply the vector U, it should be no different than the vector being multiplied individually by A and B and then added together. The ninth property is known as the associativity of the scalar multiplication, which says that if you multiply two numbers first and then you multiply the resultant number to a vector, then the resultant vector should be no different than if you multiply the vector by B first and then you multiply the resultant vector by A. Finally, the 10th property is so-called existence of scalar multiplicative identity. In summary, to define vectors, first we need to have a set of numbers, either set of real numbers or set of complex numbers. Second, we need to have a set of mathematical objects which satisfied all 10 rules together with the set of numbers that we have discussed. Then the second set, we have denoted it by capital V, is called linear vector space if it has two operations, that is addition of vectors. Second, scalar multiplication. If you have these two operations and all the elements of the set capital V satisfy these 10 rules, then we call the capital V to be a linear vector space, and all elements of the set capital V are known as vectors. I hope you have enjoyed today's session. In case you have a question, comments, or a suggestion, please feel free to write them below in the comment section. And if you would like to follow the physics discussion here, then you are welcome to subscribe to this channel.